What's going on, everybody? Welcome back. This is the very beginning of homework 2. Super exciting. We're going to be working on a new set of problems together. I have a question for you today. Have you ever woke up in the morning and you just thought to yourself, if I were in the ocean and I had like a rope or a chain or something, how far down could I let this chain go underwater before it broke under its own weight? Well, I can tell you that I thought that very thing, and that's the kind of question we're going to be solving today. So, we have our first part of our question. Derive an expression for the maximum length of a vertically suspended cylindrical steel cable, constant radius and density when submerged in water. That's the question I just proposed to you. And then there's an even more exciting solution to this problem when the radius of your chain can taper down. So that's going to be the second part of our problem. The radius can taper. Derive an expression for the optimal radius as a function of position for a cable of length L and radius of r sub L at its lowest point. We're also given for this problem that the effective density of our steel cable underwater is the density of steel itself minus the density of water. So we're going to be using this and implementing it in our equations here. All right, let's get started with number 1. Derive an expression for that maximum length. Okay, so like we normally do, we're going to draw a picture to start us off here. And just to kind of set the scene, we have our little body of water, and we were interested in dropping a rope or a cable. I guess we have a steel cable in this problem down underwater. And we want to know what is the maximum length of that cable we can have before the weight of this cable is so great that it snaps at the very top of the cable where you're holding it. Okay? So our cable here for today's purposes is a cylinder. Okay, and it has a radius of r in our first problem. Okay. So we know that the strength across a cross-section of anything for that matter is the force applied to that cross-section over the cross-section itself. And this would represent the strength signal. Okay, so where do we go? Well, we have to figure out what forces are on this area. The area is pretty simple. We know the area is going to be in variable terms, I r squared. Okay, so right away we can have an equation here for force, where force is equal to the strength of the material times pi r squared. Now all we have to do is find the force exerted on this cable due to its own weight. Okay, so well, what is weight? Force is going to be equal to the mass of the cable times gravity. But in addition to the weight of this cable, we also have the buoyant force of water, which is equal to the volume of water displaced by the cable itself times gravity times the density of water. Okay, so we have to factor that out as well. Okay, well, this is pretty simple because we know that the mass of the cable is simply equal to the volume of the cable times the density of the cable itself. So we have, sorry for the interruption, we had somebody walk into the room. I almost got kicked out, but I fended them off, and no worries. All right, so back to our expression for force. This gets really simple now that we have it in these terms. We know that the volume of this cable is going to be equal to the area across the cross-section of the cable times its length. That's what we're interested in finding, maximum length. Okay, so that's really simple. We can substitute all this back in and factor out what we need to factor out. So we get force is going to be equal to volume pi r squared L max times, let's do this here, the density of steel times gravity minus pi r squared L max. Again, that represents the volume of water displaced by the cable. That's the density of water times gravity. Okay. Apologize for another interruption. We had yet another person walk into the room, and once again, I fended them off. So, gotta get a lock on this door. All right. Finally, back to our expression for force. We can begin to factor out what we need to factor out here. So we have pi r squared L max and g, and then we're left with just that density of steel minus density of water. And like I said, we're given in this expression that the density of steel minus the density of water is equal to the, we're going to call it the effective density of steel in the water. So we can just, these would be terms you can look up or know off the back of your hand, but we're going to replace this with rho sub E for the effective density. All right. Now that we have that in place, we have an expression for force, and I believe we can substitute this all the way back into our original expression here. And we get the strength of material times pi r squared is equal to pi r squared times the length times gravity times the effective density of steel and water. Very clearly, our pi r squared cancels out, and we're left with, and we want this as an expression for L max. L max equals the strength of the material divided by G times the effective density. That's it. That's our expression for part one. The maximum length of the steel cable. So I'm going to go ahead and write that down. Save that for later. L max equals strength over G rho c. Okay. Done with part one. Make some more room here for part two. And my marker's dying. Both of these are, so I'm going to grab a new one. All right. So now, part two, we have the radius of our rope now can taper. We want to derive an expression for the optimal radius as a function of position for a cable of length L and radius of R sub L at its lowest point. So basically what that means, let's draw a picture again. We have our water line here, and this time, instead of just a straight down cylindrical cable, we have a cable that can taper underwater. The reason it would taper like this is as you go down, less and less weight has to be supported underneath it. So at the top, you have to support the entire length of the rope, and as you go down, maybe right here, you only have to support this length of the rope, so it can get narrower. So this is a little bit more tricky. How do we solve for an expression? We're looking for an expression for the optimal radius as a function of position. And we're going to call this position, we'll call this the z-axis, like depth z, and we'll call down the positive z direction. So we're looking for a function r of z. Okay, and that's going to describe our radius for us. So again, recall that our expression for force we came up with was sigma times pi r squared. But this time, the forces are going to be a little bit different. Since the volume is not constant along this width, we have to do some integration. So let's go ahead and move this to the other side just so we have some more room on this. Okay, so we need an expression for the volume of this shape. We can use the disk method if you're familiar with that from Calc 1 maybe, or Calc 2, I don't remember, where we can integrate our area along the length. So we'll call this, we really are interested in like going from a depth of z to the bottom, right? So any depth of z back to the bottom. So we'll go from z to L. Okay. Let's do that. Okay, so now we have our volume here. Times, what do we have before? G and the effective density, right? And of course, we can't forget dz there for our integration. Okay, great, so we have this. Now, how do we go about solving this? Well, we can use a little trick where we take the derivative of both sides, and that comes from the first fundamental theorem of calculus. So, we'll take the derivative of both sides with respect to z, and that's going to eliminate this integral for us that we can't solve yet. All right. Taking the derivative of this side, we get strength as a constant, pi as a constant, then we get 2r, don't forget the chain rule, dr dz equals, now, how do we go about taking the derivative of this integral expression? Well, we have to be careful here because this is actually a decreasing function. If I were to draw us a little chart here, we'll call this depth, okay? Okay, and then we'll call this radius. As depth increases, going down, our radius decreases, right? Looks like this, it tapers. Okay. And so when we're going from some depth, say z, down to some depth L, okay, what happens is by going across our differential unit here, we've actually decreased the area under this curve. So when we take this derivative and integral, you might think they just cancel out. Well, they do, but they leave a negative sign behind, and it's because this function's decreasing here by that differential unit. Okay, so now, these kind of, we can get rid of, right, but they leave a negative behind. They leave a negative with respect to that r squared. Okay, and then we're left with our constants still over here, those states. Okay, so that's an accurate expression. We can do some cancellations. Pi cancels. This r cancels with this squared, one of those r's. And now we can kind of reconfigure this expression into an expression that's integratable now. So I'm just going to rewrite this for clarity. We have sigma times 2 times dr dz equals negative rg rho. All right. Still not integratable. We need to get our units here on the right side. So let's go ahead and do that. We need r on this side, dz on the other side. dr divide by r equals we got negative g times rho e over 2 sigma, and then of course don't forget dz. Okay, now this expression we've separated, and now it's integratable, right? So we can take the integral of both sides here. Now, again, tricky. What are our limits of integration here? Well, for r, we want to go from RL, its lowest point, up to some original r. Call that r naught. Okay. Then, for z, we want to go from z equals L to z equals some z. Okay? Z equals L up to some value of z. Doesn't really matter. Since we're going up to some value of z and we're using the limit of the variable here as z, we shouldn't really do that. So we're going to substitute a dummy variable in there for z. We'll call it z prime. It's correct notation. Okay. We can go about integrating these now. So the integral of dr over r on these terms is going to be equal to, and I'm gonna start up here. We get the natural, oh my goodness, my marker's getting a little faded. The natural log of r evaluated from RL to R naught. Okay, this equals negative G rho E over 2 sigma, and then Z, which is evaluated, from L to Z. That's Z prime is evaluated from L to Z. Okay, substituting those in, we get the natural log of R naught minus natural log of RL equals, let me switch markers again. See if this one works anybody. Negative G rho E over 2 sigma times Z evaluated from Z to L, Z minus L. Okay, sorry for the color change. My markers are dying, I need to buy some new ones. All right, remember from our log rules that the natural log of A minus the natural log of B is equal to the natural log of A over B. Okay, and then this is set equal to this still. What I'm going to do is take this negative sign and distribute it, and what it's going to do is just switch these variables around. We'll get a positive expression. It's a little bit easier to handle. So we get now L minus Z over 2 times the strength. Okay, that looks correct. Got a good expression there. Now, let's see. Okay, so we can get rid of this natural log here, right? Take the exponentiate both sides. So if we take e to both sides, these cancel out. Okay. Now we're looking for this, remember, as a function of z, which I think we've got now. So we got r is equal to the minimum radius, bottom, times e to the power of g rho L minus z over 2 sigma. Okay, and I think that's our final expression. When I write exp, just this equals e to the power of the thing in parentheses, right? Okay, that's our final expression there. Looks like we've accomplished 1 and 2. Thank you for joining me for homework 2, part 1. I'll join you again soon for homework 2, part 2. Sorry about those interruptions earlier in the video again. And I think that's it. We'll see you next time. Thank you.